Okay, so this is PreCalc 3.4 day 2, and yesterday we finished right here, and Friday we finished right here, and I had y'all answer on your own. Now, right now you should be looking at that and seeing what you answered, and I have my reasons for why it's not. So are there any questions about what's up with these? We okay? Yes, no, we're not surprised. Remember, today what we're doing is we're using properties of logarithms to expand and condense. We're going to use change of base formula today. I know it was on the assignment yesterday. And we'll be graphing logarithmic functions of base B. And we're not going to do the re-expression of data, okay? But I will look at a solving, expanding, condensing thing at the end here today. So, next thing. Although some of you have calculators which allow you to change the base of a logarithm, currently most of us do not. I guess that really should be currently we all do, okay? And it shouldn't be, although all of you, okay, we all have change of base. You guys know where that is? It's like log base, I think that's what it is. I just want to make sure you all have it on your calculator, and my calculator didn't come up when I popped that up, so let's get that show on the road. Open up your calculator, go to math, or borrow one of the ones I have in back. By the way, speaking about borrowing calculators, if you have borrowed one of my calculators in the past because yours didn't run or work or come out real nice, please do me a favor and check your backpack, because I'm going to be honest, the calculator I'm missing is probably in your possession. Okay, you don't intend to do that, it just happened by an oops. So if you can correct that oops, I'd greatly appreciate it. Now, here's the thing. Let's go to y equals. I'm going to get rid of these. Excuse me, clear. Answer. Okay, that's all off. Now, I'm talking about change of base. So I'm back here at second quit, and I want to go to math and go to A, but I'm just going to factor up. Hey, log base. Look at that, log base. And people are like, dude, look, Bloom's got like this really cool Ford or something. He makes a logs. It's his log base. No, it's log base change. Okay, so I can actually put that in the main calculating area of my calculator, or I could use it in my graphing portion of my calculator. It's some pretty cool, nifty, thrifty stuff. So this problem that we're looking at, this log 4 or 7, log base of 4, I could put that 4 in, I can put in 7, you can too, and I could enter. Okay, now because it is a log base 4 of 7, I could also use common log of 7 divided by the common log of 4. And I could hit enter. Wow, crazy, that's the same answer. What if I did the natural log of 7 divided by the natural log of 4? No way! I got 3 ways to do the same answer. Happy days. Okay, just make sure you don't mix stuff around. Okay, so that's what's going on with these. That's how I got this stuff, maybe. Okay, so remember, the top gets the argument 7, the bottom gets the base. The base, hey, it's all about the base. Wow, that song, it really comes back a lot, don't it? It's all about the base for Bloom. Okay, so now we got this rule, change of base formula for logarithms. We just found out that the natural log of, well, I don't want to go with the natural log because this is talking about the change of base where our new base is A, whatever that base might be. But I suppose I could go, hey, log of X over the natural log of B, and that would also be just for a natural log base, or I can change it for any base. But you'll notice that these are the 2 most prominent ones that we use, the popular ones. Okay, those are the popular kids on the block that get used all the time. Okay, big surprise. Okay, not a big surprise. Eye rolls for the big surprise. Okay, so your turn. Go ahead, use it in using common logs, and give me that. I know you can pop up the, your calculator, but actually these are shorter and faster if you actually figure them out this way using your calculator versus going into math and bringing it up the other way. So get her done, done. I was just admiring his calculator that's online. Okay. Are you okay with these? Yes, no, maybe. We're doing okay. We're all righta. All righta, Ida. Okay, so now we're doing change of base. Because we're doing change of base, there are some properties that extend to it. Now, graphs of logarithmic functions with base b. That's what we're looking at. And we're gonna get rid of some stuff because this is a, I guess I can't get rid of stuff, but we're gonna try. Because some of this stuff needs to go bye-bye. Okay, now, using change of base formula, we can rewrite any logarithmic function g of x equal to log base b of x as g of x natural log x over natural log of b, which is now expressed as a vertical compression by a factor of 1 over the natural log of b times the natural log of x. So I've got the parent function natural log of x, and now to get to that next one with that change of base, I can say that natural log of x would have to go under a vertical compression by a factor of the 1 over the natural log of b to make this work. But now, therefore, every logarithmic function is a constant multiple of a natural logarithmic function. Okay, totally can work. Now, if the base b is greater than 1, the graph of g of x is equal to log b of x. Is a vertical stretch or shrink of the graph f of x, natural log of x. Now, check that out, if my base is between 0 and 1, a reflection across the x-axis is required as well. Okay, that's crazy talk, I tell you, but it kind of makes sense if we talk about this. What that just means is this. If I ask you to do the log of base 1/2, okay, base 1/2 of, say, 2, okay, that's the same of, let's just say of x, okay. If I do this change of base, they're saying, well, you know, in the change of base bloom, this is the natural log of x over the natural log of 1/2. But according to that stuff we just underlined, this is true, that I have the negative natural log of 2, notice the switch, times the log of x. What's the exponent difference between 1/2 and 2? Base 2 wise. Isn't it -1? That's crazy if they're reciprocals of each other, and that, wow, I wonder if there's a connection there. Exponents, crazy. But let's look at this and see what's going on. Okay, so looking at this, I have my natural log of x graphed, okay? And remember that natural log of x, I tried to do them perfectly, but you know, I can just do so much sometimes. Let's see if I can get rid of these green things so you guys don't have to deal with that. Let's get rid of this green thing. Wow, that's crazy. Wrong green thing. It's really not letting me get there. Okay, it'll be fine, I guess. I'll have to adjust to it. Get back down there. So that's my natural log of x. Okay, that's the function that's already there. That's my parent function we're working with. Okay, so the natural log of x will cross the graph at 1, 0. Okay, it will also come across at a little less than 3, 1, because remember it's 2.718, you know, my e, so it'll be a little less than 3, it'll be like here. Okay, and when I square it, if I do that times 2, it's less than 9, so it's a little less out here, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, so it's a little less there, and it's at 2 right there. So I got my points. I'm gonna make it a better point. Maybe I just put a dot. That might be better. I'll put a dot here. We'll just make that dot smaller. Nope, can't do it. Cut that, put a better dot. And then I'll adjust. Okay, so I got my dots. Okay. Are you okay with my 3 dots? Fantastic. Now, keeping in mind, I have the natural log of x graphed. Okay, and they're asking us to represent the g of x equal log base 5 of x, okay, as a transformational graph of the natural log of x. So when we do this, we do the change of base function. Okay, so this rewrite should be in natural log, so I should have 1 over the natural log of 5, natural log of x. Okay, natural log of 5, natural log of x. Are you okay with the rewrite? Yes or no? Matter of fact, while we're busy, I'm going to talk about the natural log here. This would be the natural log of 1/4, the natural log of x. Now, because it's a natural log of 1/4 and it's between 0 and b, okay, my graph will go through a reflection across the x-axis, but in order to describe it better, it's not a reflection across the y-axis, or excuse me, the x-axis, followed by that vertical stretch of natural log of 1/4. It is the reflection followed by that natural log of 4, okay, times natural log of x, okay? So now, with that said, I've got my transformations to talk about. I got a vertical compression by a factor of 1 natural log of 5, and I've got a vertical reflection followed by vertical compression by the factor of 1 over the natural log of 4. Okay, those are my 2 graphs I'm going to work with. Now I'm going to let you in on a secret. I'm not graphing these with a calculator. I'm graphing these without a calculator. It's faster. So I'm going to use the base prior to the change. That's easier than doing the base change formula with the stretches and everything, because I'm not going to have a calculator to talk about my stretch of 1 over the natural log of 4. That's impossible for me to graph without a calculator. But I can graph this function, so let's talk about that. If I'm looking at my value of my function, they asked me to express my transformation, but I want to talk about graphing because it always helps for us to practice, right? Okay, so y is equal to the log base 5 of x, okay? And this is a real nice straight up deal to do. If I put in 1/5, I get out -1. I put in 1, I get out 0. I put in 5, I get out 1. Okay, so I've got 1/5 -1. Okay, 1/5 -1. Okay, I've got 1 0. 1 0. Hey, that's like right on top of that one. And I got 5. 1 2 3 4 5 1. Okay. Now, remember we came out as a vertical compression because it was going to be shrinky, right? So my graph comes through here, comes up, and comes across here underneath as I go up. And this is my graph, y equals log base 5 of x with that vertical compression component in it, okay? Now, are you okay with how quick that was for me to graph using the powers? Okay, same idea, going off. We're going to graph over here, the same idea, okay? Are there any questions about what I did over there? The graphing by hand. You will be asked to do the graphing by hand on the test. I want to make sure you have no questions on how to do it. And that'll be no calculator. By the way, on Friday next week is the no calculator portion of the test. We have a half-hour class. The test that part of the test will be a half hour. So be ready for it. Okay, one and done. We're over and out. Okay, I went through it today and it took less than 10 minutes, so it should take you guys less than a half hour to get it done. I'm pretty confident about that. I ain't no brainiac. Okay, I just continually do the same thing over and over again, practice. Okay, so here's the deal. In this second one, I got the transformation, but I'm still graphing based on the original because it's easier to graph. Does that make sense? So we're going to talk about how easy that is to graph. I've got the, now remember, I made that change. So y, the inverse of 1 over, no, we won't make the change. Let's just go for it. Log 1/4 x. Okay, so I got 1/4. So I put in 1/4. I get 1. I put in 1, I get 0. I put in 4, I get -1. Okay, you okay with where I'm going with that? I put in 16, I get -2. So over here, I've got 1/4. 1/4, I got 1. Where's my 1/4? I got 1. Okay, I got 1, 0. I've got 4, 1, 2, 3, 4, -1. And that's my graph. Now, keeping in mind, this is my asymptote for both of them. And for this one, this is my asymptote for both of them. Okay? That makes sense with my reflection in my vertical compression, right? So I look over that graph. Are there any questions about what I did graphing? We're going to graph 2 more times. We're going to graph the same way, so get ready for it, man. Okay. So now, what I just used over there, we have right here. Hey, that opposite, if I take the reciprocal of the base, totally works. That's what we're going to do. We don't use it a lot. But let's talk about logarithmic functions, base b in general. Okay, this is covering just about all logarithmic functions so long as b is greater than 1. If it's less than 1, it's going to look a little different. Okay, you just saw what it's going to look like if it was less than 1. It'll come down, it'll decrease along the function. But here, generally, if b is greater than 1, they're all reals. The domain's from 0 to infinity. It's increasing on its domain. The symmetry is neither even nor odd. I want to review symmetry. Odd symmetry. Okay, a symmetry that when I put in the opposite of f of x, I get out f of x. Even symmetry. If I put in the opposite of x, I get out opposite of f of x. Okay. Now, in this, I've got even and oddness going on here. I just wanted to make sure you get that in as review. We're going to be getting to the final, but just keep in mind, that's why when I say, hey, symmetry, even odd, that's where I'm going for. It's not bounded above, nor below. There's no local extrema. There's no horizontal asymptote, but there's a vertical. Yes, dear. Oh, I think I lied. I hate it when I lie. I lied like a rug on that. You're correct. I hate it when I flip that around. Somebody's just gotta undo his whole life here. So when we're talking about even, and I'm not sure why I went in even. Even should be the same. You're correct. Thanks, Fleur. I appreciate it. Okay. And that should be f of x. That should be the same. Because that way I've got the same going both top and bottom. Let's talk about odd. Should be the opposite because we have things that do that. Okay, so thank you. Thanks for doing that. I think it was earlier I just did it even and odd, and I wrote odd this time for some reason. That was odd of me, wasn't it? And it wasn't something for the setup of that joke. It was really bad. Anyways, so we got that clarified. Okay. Looking at this. Holy cats. Nothing got saved from earlier. Okay. We had a few issues with my stuff, I had to redo stuff. I have no idea why it's funky, so funky, but we're hoping that that doesn't restrict us from other things today. Now, we're going to do some examples with graphing. And what I want you to be aware of, you will have a no calculator portion of the test. You will be expected to graph a log without a calculator. If you've been relying on it, I've been telling you not to, well, you know, here's my example for making sure you are. I'm going to do this one on the right because it's possible, but not impossible. It's just that the one that's more like the test is the one that's an A, okay? I might give you one, but I won't do anything really super funky with it. But I want you to watch the rewrite because rewrites might be in there because I expect you to be able to rewrite. So when I'm looking at this function, when I'm trying to read these, there's a couple things going on. First, I'm looking at this and I've got, well, you know, this is, if I undo, it's the opposite of log base 2, okay? Notice I did reciprocal, took the opposite. That means it's a reflection over the x-axis right now. I'm putting the 2 to the end of my function. Inside here, let's change colors. Inside here, I have the negative x minus 3. That's the rewrite, okay? My end is plus 2. So my g of x, to help me graph faster and easier, is written out that way. Okay, so let's talk about my transformation. I'm going to reflect across the x-axis. So I have an x-axis reflection followed by a y-axis reflection. I get my reflections out of the way. Then I move horizontally 3 units to the right. Vertical 2 units up. Okay? So are we okay with those? Yes or no? Now, I'm just going to use that with my parent function. Now, I did a rewrite of log base 2. So my parent function now is log base 2. So let's look at what my parent function is. Okay, so I've got x, I've got y, I've got log base 2. I'm just going to remind myself it's log base 2 of x. Okay, that's what it is. So I put in a half. I'd put in a fourth, but you know, it's still something small, but it's really tough. So I'm going to put it in a half, I get negative 1. I put in 2, excuse me, not 2, but let's put in 1. I hate that when that does that. Okay, we'll put in 1 eventually. 2, I get positive 1. I put in 1, I get 0. I'll put in 4, I'll get 2. I'm a little out of control with that, but we'll talk about it when we get there. So this is my function going across. We're going to get rid of that. We're going to unlock this. This is not my parent function that I'm worrying about. Cut. Okay. When I'm looking at this, I'm interested in that parent function. So I've got my 1, 0. I've got my 1/2 negative 1. I've got 1, 2, 3, 4, 1. Was it base 4 or base 2? Base 2, sorry, apologize. 2, 1. And now it's 4, 2. 1, 2, 3, 4, 1, excuse me, 1, 2, 3, 4, 1, 2, and 8, 3 I can do. That's 4, 5, 6, 7, 8, 1, 2, 3. So this is my original parent function. Coming up here, that's what it's looking like. Oop, kind of took a wrong turn there. Okay, so my parent function is doing that. Are you okay with that? Now I'm asked to graph the change to that parent function. So I'm going to put in these two first. According to our transformational directions, our rules that we just found, I'm going to bring those down so I can see them. I'm going to bring up the graph so you guys can see that instead of my back. I'm going to do my best over here so you guys just know what I'm going to do, and I'll flip-flop. But my first one, y-axis reflection, no problem, it doesn't move. Y-axis or x-axis reflection, no problem. Y-axis has got to go 1 unit, right? Then it's going to go horizontal 3 units right, 1, 2, 3, up, 2, 1, 2. That's my first move. Okay, so that's this one. My next one we'll do here, just get out of the way. I've got a x-axis reflection, that's 1, a y-axis reflection, 2, back 3, 1, 2, 3, up, 2. Now at 4, that was my 2 spot, my 4, 3, 4, 1, x-axis reflection, 2, y-axis reflection, 4, 1, 2, 3, 4, back 3, 1, 2, 3, up, 2, 1, 2. Now I haven't reflected this one yet. X-axis reflection goes up. Y-axis reflection goes over that half. Back 3, 1, 2, 3, up 2, 1, 2. Okay. Now I've got 8, 3, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, right there. X-axis reflection, 3. Y-axis reflection, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Back 3, 1, 2, 3, up 2, and I'm there. So here's the deal. I'm looking at a function that's coming through here. Its asymptote is right here at x equal 3. Okay? Does that make sense? Now, with that said, that's where I'm sitting, right there. I've got this graphed coming through here, and now I can talk about some pieces of information. I'm just going to bring these directions down so we can talk about the asymptote. Asymptote is x equal 3. The y-intercept. Y-intercept is when x is 0, right? So I got to plop in x is 0 here. So this is going to be opposite of log 2, 3 plus log of 3 base 2, I should say it that way. So I put that in my calculator and I come up with 4.415, and people are like, how did you put that in your calculator so quick? We didn't even see you bring up the calculator. So remember, it's opposite of log 2, 3 plus 2. So opposite of my change of base, I'm going to grab that. Okay, go up, log, base. My change of base was 2 of 3, and I'm going to add 2. That's that 0.415. Okay, now here's the thing. If I'm having you graph this without a calculator, I wouldn't have you find this if it were something that was this difficult. But the one I'm going to have you work on isn't that difficult. It comes out pretty nice. So just keep that in mind. So I've got that all set, and that's how I was able to get that. Now my domain. Let's talk about domain. Domain of my green function goes from negative infinity to 3. Okay. My range of my green function goes from negative infinity to infinity. And my end behavior as x approaches negative infinity is going to be negative infinity. That should be negative infinity. I'm not sure what I did wrong here. I think they just kind of absorbed each other. Megacurs, mergers. I get a kick out of that, so we're just going to get rid of that. We're going to cut that, and we're going to go as x, the limit, as x approaches infinity of my, I think the function is g of x here. G of x. So I'm going to make sure I'm g of x. It goes to negative infinity. As I approach negative infinity, it goes to negative infinity. Okay. When I approach positive infinity, it stops at the wall. So that's not anything I'm worried about. Now it's your turn. Okay. You guys give this one a try. All I want you to do is come up with the parent function, do the parent function, and then manipulate the parent function. Please do that. clean this up so I can do mine a little faster. You guys are waiting? Because you guys are just practicing. Or not. Let's get back there. Okay, good. Remember, your parent function is log 3 of x. So 1/3, 1, 3, 9. So -1, 0, 1, and 2. -1, 0, 1, and 2. 1/3, -1, 1, 0, 1, 2, 3, 1, and 4, 5, 6, 7, 8, 9, 2. Okay? Now, that's my parent function. That's all I did. What I want you to realize is that we're going to go and graph our parent function based on our transformations. Okay? You have an x-axis reflection. And then I'm going to move left 1 unit. Okay? Well, that's what I'm going to do with my points. So x-axis reflection, left 1 unit. You know what's really cool about that, since it's just left 1 unit? I am going to clone that real quick and put it on top of it. So we are going to flip it up and down. That's my x-axis reflection. And from here, that's where we're at right now. Are you all in agreement that that is pretty much my x-axis reflection of my function? Now I'm going to go 1 unit to the left. Okay, in doing that, I also pull, I pull my asymptote with me for that 1 unit to the left. Now, keeping in mind with that, everything was going to go. This was going to flip, stay here, and just go back. This goes from here, down here, over 1. This goes here, down here, back 1. So that's where all those things are coming from, my old points, if I translate it that way. Does that help visually? Okay, pretty nice, slick way to graph. Okay, when we're getting it done transformationally. It will work if you put in powers and that too, but I like doing it this way so you guys see the log. Now, with that said, asymptote, x equal -1. Y-intercept. Y-intercept was 0, 0, so was the x-intercept. Life was good. Domain, -1 to infinity. Range, -infinity to infinity. And behavior. Okay. Are we doing okay? No surprises. Okay, next problem. Here's the thing. You're going to be working with different logarithms, values, and I'm hoping you're starting to recognize the argument inside the log is the thing that restricts your function, your values. Okay, so I can extend this out, maybe move this down here so I have room. I'll move this down here too, and let's see if I can move this without touching it. We'll see if that works. So you ready? I have a rewrite, kind of. So I got -5 natural log of x squared minus 16 plus 2. But you know, I could care less about the rewrite because right now I know my domain. My domain restriction's really all about x squared minus 16. And we did something like this last week. I want you to know that when x squared minus 16 is greater than 0, that's important. That's where my domain exists. Okay, so if I'm thinking, hey, sign chart. So I've got x minus 4, x plus 4. So I've got negative 4, 4, and I'm going across here, here, and there, and I'm talking about from negative infinity to negative 4. Can't include negative 4 because then it's 0. And from 4, can't include it, to infinity is where this domain exists. So I'm looking at my domain as being from negative infinity to 4, negative 4, and from 4 to infinity. And I'll get that other junk out of your way so you don't have that across to deal with. Okay, does that make sense where I got those from? I have the answer for the other one up there, and I apologize that I had to pull this up from a different thing, and I had edited it earlier, but my edit didn't get saved because I had to dump things. But here's my concern. Again, this has to be positive. So 4 square root of x has got to be greater than 0. So let's rewrite. I got this plus 4. It's got to be greater than 0. What if I'm looking at this? This is a reflection of the square root function, right, over the x-axis, and I bring it up 4 units. So if I'm really thinking about this function in itself, and I'm talking about this pretty much, it's going to be rising as I go. Actually, that's not going to rise at all. It looks pretty horizontal. Let's do that again. Yeah, it looks better. Now, if I flip this, and I'm going to clone it, and I'm going to flip this up and down. So I'm flipping up and down. So I've got this flipped, okay? Now I'm going to bring it up 4 units. 1, 2, 3, say that's my 4 units. Say that's 4 today. Because down here, that's 4 units up, and that's 0, 4, okay? Totally going to work there. Over here, okay, is going to be 16, 0. Now let's look that over, and are you in agreement that that's 16, 0? I put 16 in there. The square root of 16 is 4. Okay, the opposite of 4 is negative 4, plus 4 is 0. But my concern is, I know it's not drawn the scale. It gives you at least an idea of the visual. Because it's inside a log, it has to be positive. So it's all good until here, and it has to be open, right? Now, keeping in mind, I can't put anything below or to the left of the x equals 0 line because I'm dealing with a square root, and I put a 0 in there, it works, but I put anything negative and it bums out on me. It's like, no, boom, you can't do that, okay? Because you can't take the square root of a negative value and get a real value out. So that's why our domain can include 0, because it can be exactly 0, but it can't include 16. So that's why we come across that. Now, does that make sense with my domain restrictions? Now, the next things. We are going to do some re-expression. Really cool. Talk about Kepler's law. Don't have enough time. Still don't have enough time. This is Kepler's law stuff. This is example 7 stuff. We're going to go to the extra example. Okay, so in the extra example, our last page, very bottom. Okay, so the bottom part, this is our last thing for today. I want you to realize that Ebbinghaus's law of forgetting states that if a task is learned at a performance level, P sub naught, performance level being above 90%, then after a time interval T, the performance level P satisfies this model. Log of P is equal to log P naught minus C log of T plus 1, where C is a constant that depends on the type of task and T is measured in months. So we got to solve for P. That's our first thing. And then our second one is if your score on a math test is a 90, what score would you expect to get on a similar test after 2 months? Okay. And then I ask after a year. But for this testing, our C is found to be 0.2. We didn't find C, it was provided to us. This is information we get to use. But before we use that information, we've got to solve for P. So we're going to do some condensing manipulation. Okay, I know that this log P naught minus C log T of plus 1 can become something a little different. So right off the bat, I know that I can rewrite this to be P sub naught T plus 1 raised to the C power. Are you okay with my condensing in my logs? Okay, and this is, by the way, log of P. Remember, we condensed in one fell swoop, we expanded in one fell swoop on Friday, and I just did it in one fell swoop. Are there any questions about my condensing of that phrase or that relationship? Now, if the log of P equals the log of P naught all over T plus 1 quantity to the C power, isn't P the same as P naught divided by T plus 1 over, the C power? Aren't they the same? So I can actually say that. Okay, I can say that that is the same because of the idea of 1 to 1. If I take the log of both sides, before I took the log, I could undo it, and P should be equal to P sub naught all over T plus 1 raised to the C power. Now, knowing that, let's answer our questions. And remember, in this problem, C was -2, or -2, 0.2. So, and P naught would be our original math test score of 90. So you got a 90 on the test. Evaluate. Evaluate, solve for T. Okay, so what's that mean? Oh wait, I'm saying 2 months, and T is 2 months in time in months. So here T is equal to 2. Okay, P naught was equal to 90. So my next thing is I put in 2, and I get 90 over 3 raised to the 0.2 power. Take your calculator and pop that bad boy out. Now, this totally assumes you have not reviewed. You took the test, you come back to it, no review whatsoever, and you take the test again. Okay? And consequently, you score a 72.24%, 247%, because this is out to 3/10. Now, let's assume that you decided, nah, I'm not going to take the test today, because taking the test today would be reviewing. Okay, we're not going to take the test today. We're going to take it 10 months later. Okay, so now our T is 12 months. Okay, if I were to do it later, now 12 months out, okay, for the first time, because I wasn't there for the first review, okay, I then evaluate a 13 raised to the 0.2 power. What's the projection of success for this test for me? Not pretty. 53%. Okay. Okay. All right. 53.88. So after 1 year without review, retention is 53.883. Now, let me let you know a secret. Teachers, boy, we look like we really know what's going on. I prep my boards. I prep my stuff. I read the night before what we're doing. I read the day before what we're doing. I read the day of what we're doing. Because I don't want to waste their time. The biggest issues we've had today has been the board. And I've had to trash it a couple times. So all my changes had to go out south a couple times. So please be it known that you got to review. We have the assignment. It's up. I think I got it on this next screen. That's day 1. Let's go to day 2 because today is day 2. And when we're working with this stuff today, please make sure you're getting your stuff done. If you have questions, please ask them. Stay on task on these. Don't get behind, because next week we have that calculator test on Friday. The Thursday, no calculator on Friday, and we're going to get rolling on that. I'm just looking to see, make sure. Yeah, we don't want to do 63 and 65. I cut those out because those are the re-expression ones I didn't want you to do. Yeah, no, just re-expression. So we're not doing re-expression. If I missed one, skip the re-expression, okay? Because I'm not going to test on it either. Okay, I think that was your follow-up. Okay, all right. So thank you for your time.